106 million cubic feet of solid rock must be extracted from the earth to overwrite the laws of geography. In a territory where the ocean exerts enough pressure to crush reinforced ships like fragile toys, engineers have devised a plan that contradicts standard maritime logic. They intend to split an entire mountain range in two to conceal the sea within its stone walls. Why spend nearly €1 billion to carve a void through granite when the open ocean stretches in every direction? A tunnel designed for ships appears counterintuitive at first glance, but in reality, the surrounding waters are among the most unpredictable environments on the planet. This investment of resources serves a singular purpose, bypassing a geological trap that has claimed vessels for centuries. Construction crews must drill into the ancient granite with millimeter precision to ensure the structural integrity of the cavern. The process is only gaining momentum. €1 billion is the estimated cost of this unprecedented engineering endeavor. The project requires the removal of massive volumes of stone to create the first full-scale ship tunnel in history. Why do maritime experts consider this mountain a more viable path than the open water? The answer lies in the unique and violent behavior of the North Sea surrounding the Stad Peninsula. On a standard map, this landmass appears as nothing more than a minor curve along the jagged Norwegian coastline. But for those navigating these coordinates, the terrain represents a lethal geographical bottleneck where the water ceases to behave rationally. At first glance, the peninsula seems inoffensive, but in reality, it acts as a trigger for atmospheric and oceanic chaos. Everything only gets more complicated when the wind shifts. One can notice how the sea state changes abruptly, as if a switch had been flipped by an unseen force. In this specific zone, weather forecasts often lose their utility within minutes, leaving crews to rely on chance rather than technical skill. Survival becomes a matter of probability as the currents collide against the underwater topography. It is visible how the waves peak and break in patterns that do not exist elsewhere along the coast. It gets more complex further on. Giant granite walls will eventually shield massive hulls from the crushing force of the exterior swells. The equipment gradually penetrates deeper into the rock face, moving away from the coastline. 106 million cubic feet of debris will be hauled away to complete the passage. This volume of material illustrates the sheer scale of the displacement required to create a safe harbor inside the mountain. The process of drilling and blasting continues around the clock to meet the rigorous technical specifications. Therefore, every inch of the tunnel walls must be reinforced to withstand the pressure of the mountain above and the water below. Thus, the foundation for the first maritime tunnel is established, moving the project toward the next phase of excavation. 30 meters is the exact height of the massive swells that transform this stretch of water into a graveyard for the strongest vessels. Why do these waves reach the scale of a 10-story building? The geography of the region creates a lethal trap where the North Sea and the Norwegian Sea collide with absolute force. This frontal impact, combined with an abruptly shallow underwater topography, generates the phenomenon of cross seas. At first glance, a storm seems like a predictable frontal assault, but in reality, these waves strike from multiple directions simultaneously. One can notice how the water acts like a colossal washing machine, battering the hull not just at the bow, but across the entire beam. The energy is sufficient to snap reinforced steel hulls in two, as if they were made of glass. But this is just the beginning. The environment does not offer seasonal respite, as storms here rarely end, instead merely pausing for brief intervals. For more than 100 days every single year, this maritime corridor remains a functional war zone. Even when the wind eventually ceases, the swells continue to roll with a lethal momentum that lasts for days on end. Records from the era following the Second World War reveal a somber and bloody statistical reality. The waters surrounding the Stad Peninsula have claimed the lives of more than 30 people and resulted in 45 major maritime accidents. It only looks obvious to avoid such a location, but for Norway, this is a physical impossibility. Norway functions as a global maritime superpower, exporting 3 million tons of fish annually to 150 different countries. These treacherous waters serve as a vital commercial highway that cannot be bypassed. Passenger ferries, heavy cargo ships, and industrial fishing trawlers are forced into a daily game of Russian roulette with the North Sea. It gets more complex further on. The logistics of the entire western coast are held hostage by this narrow and deadly bottleneck. Captains must wait for weather windows that might last 4 hours or collapse entirely in 30 minutes. It is a high-stakes lottery where the cost of entry is the lives of the entire crew. The process is only gaining momentum. The only logical engineering solution would be to sail around the danger, yet no such path exists geographically. Consequently, Norway has committed to an unthinkable architectural feat. If the surface waves cannot be defeated, the maritime traffic must be diverted deep beneath the earth. The Stad Ship Tunnel is the definitive answer to this environmental crisis. On a technical diagram, the concept appears deceptively simple. Engineers have plotted a straight line connecting two fjords by cutting directly through the base of the peninsula. In reality, this represents the most ambitious terrestrial surgery ever attempted within Scandinavia. We are not describing a standard subterranean passage for automobiles. Instead, the project demands the creation of a massive corridor. One can notice the scale of the operation as the camera glides along the projected path of the excavation. The material is ready to move to the next processing phase without haste. 26 meters is the total width assigned to the passage, a dimension calculated to ensure the safe transit of even the most robust vessels equipped with protruding antennas and specialized equipment. Why is such a vast lateral clearance necessary for a subterranean maritime route? It would seem that a narrower opening could suffice for smaller craft. But the hydrodynamic forces within a confined space mean that any ship requires a significant buffer zone to maintain its trajectory against the displacement of water. 3 million cubic meters of solid rock must be extracted by the engineering teams during the excavation process. To comprehend the sheer scale of this displacement, one can notice the logistical requirements involved in moving such a mass. Transporting this volume would require 750,000 individual trips by heavy-duty dump trucks. The mountain is being dismantled piece by piece as the complex geology of the region demands a cautious and respectful approach to structural integrity. Technicians have rejected the idea of a single massive detonation in favor of a systematic layered construction method. Instead of drilling horizontally from one end to the other like a standard boring machine, the crews excavate from the top downward. First, the ceiling of the tunnel is removed to allow for the stabilization of the overhead vault. Only after the roof is secured does the deepening of the channel begin, level by level, until the floor reaches 12 meters below sea level. One can notice how the equipment gradually slices through the granite like a giant multi-layered cake, using a combination of explosives and massive hydraulic excavators. But this is just the beginning. It only looks obvious that a blasted rock surface is sufficient for transit, but in reality, explosions leave behind irregular walls filled with sharp peaks and deep fissures. In a standard road tunnel, these imperfections are simply covered with layers of concrete. However, in a tunnel flooded with water, the extreme roughness of the walls creates dangerous turbulence. If the water flows in a chaotic pattern around the hull, a ship can lose its steering control entirely. The process is only gaining momentum as the engineers implement a technology usually reserved for precision manufacturing. Fios de diamante, or steel cables encrusted with industrial diamonds, rotate at staggering speeds to slice through the granite. One can notice how the diamond wire moves across the stone face, leaving behind a surface that is perfectly smooth. This ensures that the water flows with minimal resistance, representing a fusion of the raw power of dynamite with the precision of high-end jewelry work on a monumental scale. Building the cavern itself represents only half of the technical battle. The true challenge begins at the precise moment the engineers invite the pressure of the ocean to enter the finished structure. From here, the transformation moves to the next phase of processing. 426 million euros. This was the initial projected cost when the maritime engineering project first received official approval. Why is such a massive investment required for a single passage through the rock? It would seem that digging a simple hole would suffice for ships to pass through. But the sheer complexity of managing the North Atlantic waters requires specialized systems that elevate the budget with every technical challenge solved. One can notice how the force of a sudden torrent would instantly destroy the internal infrastructure and potentially cause the tunnel walls to collapse if the North Atlantic were to invade the space unchecked. The process of flooding the structure will therefore become the most delicate hydraulic operation of the current century. Throughout the entire construction phase, the tunnel will remain completely dry. shielded by temporary steel dams positioned at both ends of the passage. Within this pressurized dry cocoon, workers will install navigation and safety systems that align with advanced technological standards. Industrial spotlights that might blind captains are absent from the design specifications. The tunnel will be illuminated by continuous strips of light-emitting diodes that run along the entire length of the stone walls, resembling a futuristic landing strip. These lights do not serve a purely aesthetic purpose. They function as the primary navigation system. In a closed environment of solid rock, global positioning systems can often fail or lose accuracy. Therefore, captains will guide their vessels by following precise colored lines of light that indicate the safest trajectory through the mountain. It gets more complex further on. The flooding process begins only when every internal system is fully calibrated. Special valves will open to allow the seawater to enter with extreme slowness, balancing the pressure ton by ton against the concrete and rock. Only when the internal water level is perfectly identical to the external sea level will the steel dams be removed. And then, the sea will be inside the mountain. But this is just the beginning of the operational challenge. How do engineers control ships weighing thousands of tons within a narrow stone tube? The tunnel will operate using a strictly regulated one-way traffic system. Vessels will travel northward for 1 hour, and then the flow will reverse to the south during the following hour. A dedicated vessel traffic center will monitor every movement, functioning exactly like an airport control tower. Radar, thermal sensors, and infrared cameras will supervise every inch of the passage. The process is only gaining momentum. If a vessel stops for any reason, the automated system will detect the anomaly instant by instant. The entrance to the tunnel represents a masterpiece of defensive engineering designed by the architecture firm Snuheta. It is visible how the entrance is not a simple opening, but a complex structural interface. The mountain slopes will be carved into staggered stone terraces that rise in levels. This design is not merely for visual impact. These stone steps function as kinetic energy buffers, breaking the force of the waves before they can penetrate the tunnel interior. The equipment gradually integrates with the landscape to manage the environmental loads. It is engineering learning from nature to tame nature itself. At first glance, the price of 426 million euros seemed high but manageable for such a breakthrough. However, the complexity of the task ensures that the project remains a high-stakes endeavor. The final cost reflects the precision required to prevent a catastrophe. This concludes the phase of structural preparation and the integration of internal safety mechanisms. The transformation moves to the next phase of processing without haste. 880 million euros is the staggering figure that the final budget for this engineering undertaking has reached. This amount represents exactly double the initial financial estimates, driven upward by the relentless pressure of global inflation, unforeseen geological complexities deep within the rock, and the soaring market costs of raw materials. Why would a nation commit such a vast sum to a single passage? The question triggered a severe political crisis that resonated through the corridors of power. The Norwegian government initially responded by freezing the entire project. Officials openly questioned the logic of spending nearly 1 billion euros simply to shave a few minutes off a maritime journey. But the parliament eventually intervened with a different perspective. They recognized that the value of this corridor is not measured in minutes, but in national strategy and long-term survival. Negotiations with contractors were subsequently reopened to scrutinize every cent of the expenditure without compromising structural safety. A definitive green light for the continuation of the project is now anticipated by the year 2026. Physical limitations remain a fundamental reality of the design. The tunnel is a massive structure, yet it is not infinite in its dimensions. One can notice how the largest container vessels in the world, specifically those belonging to the Panamax class, are far too wide to enter the portal. These giants of the global economy will continue to navigate the violent storms of the open sea. But this is just the beginning. The tunnel was never intended to accommodate the largest oceanic transporters. It was designed specifically for the coastal fleet, the essential vessels that maintain the logistical lifeblood of the Norwegian coastline. Analysts estimate that 81% of all current maritime traffic in this specific region will be able to utilize the sheltered passage. Economic efficiency will stem primarily from fuel savings and the establishment of absolute regularity. It seems simple at first glance, But in reality, the hidden costs of the current route are immense. Today, ships are forced to burn tons of diesel fuel while battling massive waves or remaining anchored for days, waiting for the weather to clear. The tunnel effectively shortens the route, but the most critical technical factor is that the engines no longer struggle against the resistance of the open ocean. For smaller vessels, the reduction in fuel consumption can reach 60%. The process is only gaining momentum as a major environmental initiative. This is a green victory encased in millions of tons of reinforced concrete. One can notice the immediate benefits of reduced emissions and the elimination of cargo risks. Deliveries are guaranteed regardless of the weather outside. Fish reaches the market in its freshest state, and passengers arrive at their destinations safely. If this project appears to be madness, it is only because the unique engineering culture of Norway remains misunderstood. This is a nation that treats solid granite with the same ease as if it were soft butter. They do not merely construct tunnels, they are technologically obsessed with them. Over 1,100 road tunnels currently pierce the rugged Norwegian landscape. 50 of these structures dive directly beneath the ocean floor. For the citizens of this country, entering the darkness of the earth is a banal occurrence, as routine as a trip to the local supermarket. They hold engineering records that would cause experts in other nations to hesitate. Everything only gets more complicated as the scale increases. 24.5 kilometers is the total length of the Lærdal Tunnel. It currently stands as the longest road tunnel on the planet. Driving from one end to the other requires 30 minutes of continuous underground travel. To prevent drivers from falling into a state of panic or succumbing to fatigue, engineers applied advanced lighting psychology. Every 6 kilometers, the camera glides along massive caverns illuminated with a brilliant blue light. This specific spectrum mimics the dawn, effectively deceiving the human brain to maintain alertness and a sense of calm. The Rogfast project represents the next level of this subterranean ambition. Engineers are currently constructing the deepest underwater tunnel in the world, descending to 392 meters below the surface of the sea. The water pressure at such a depth is mathematically crushing, but the depth alone is not the most impressive technical feat of the project. Down there, in the pressurized darkness of the seabed, they are building structures that seem physically impossible. This includes the construction of full-scale traffic roundabouts located hundreds of meters beneath the waves. One can notice how vehicles will navigate these junctions nearly half a kilometer below the ocean. This continues the long tradition of Norwegian mastery over the subterranean environment. 100 feet below the surface of the ocean, travelers encounter a circular illuminated intersection where the choice must be made to turn toward an island or continue toward the mainland. Why construct such a complex junction deep within the seabed? This vast city of concrete beneath the waves serves as the functional heart of a subterranean network. But this is just the beginning. The Stad Ship Tunnel is not a solitary miracle for Norway, but rather the next logical progression in a long lineage of underground engineering triumphs. They have already mastered the art of keeping seawater out of automotive tunnels. Engineers are now simply inverting that established logic to keep water inside a tunnel designed specifically for ships. It is visible how the equipment gradually adapts to these new hydraulic requirements. What comes next in this evolution of infrastructure? Norwegian ambition does not conclude with the penetration of solid rock. They are already analyzing fjords that are too deep for traditional underground tunnels and too wide for conventional suspension bridges. The solution manifests as submerged floating tunnels. Imagine two giant concrete tubes suspended 30 meters below the water surface, stabilized by pontoons on the exterior and anchored firmly to the seabed. At first glance, this looks like a conceptual sketch, but in reality, it is a calculated structural response to geography. Ships would pass over the structures, cars would drive through the interior, and waves would pass by without affecting any part of the system. If a ship tunnel is considered unusual, the floating tunnel is pure science fiction becoming physical reality. Transition to the next level. Back at the construction site, the impact of this project extends far beyond the limits of engineering. Not a single fragment of the mountain will be discarded. 3 million cubic meters of extracted rock will be utilized to construct an entirely new district in the neighboring city of Moløy. Houses, hotels, and commercial centers will rise upon the very material that once blocked the maritime path. One can notice how the human factor transforms the site into a global magnet for observation. a dedicated viewing platform is being constructed so the public can witness the surreal moment when a massive cruise ship deactivates its storm radars and glides silently into the earth. It is visible how the vessel enters the stone passage with millisecond precision. This represents the final victory of human ingenuity over the raw, unyielding force of the natural elements. Ultimately, the Stad Ship Tunnel serves as more than just a safe passage through the peninsula. It stands as a monument to technical persistence and the refusal to be halted by geographical barriers. The material is ready to move to the next processing phase without haste. Thus ends one of the key stages of this monumental maritime transformation. 30 meters is the height of the gargantuan storm waves that frequently assault the coastline, yet engineers have designed a solution through mathematics, explosives, and reinforced concrete. Why construct a passage directly through the center of a mountain? It would seem impossible to bypass the violent natural forces of the open sea. But inside the rock, a massive vessel now glides in total silence through a tunnel illuminated by soft light-emitting diode arrays, shielded entirely from the atmospheric chaos raging on the exterior. The mountain remains an immovable geological fixture, yet human engineering has mastered the ability to penetrate its core. $27 billion represents the combined financial investment required to erect two of the most significant defensive barriers of the modern industrial epoch. On one side of the globe, a steel scar stretches across 3,200 kilometers of scorching desert terrain intended to regulate human movement. Simultaneously, a titanic concrete shield descends into the frigid depths of the Japanese coastline to obstruct the physical momentum of the ocean itself. At first glance, these structures seem insurmountable, but in reality, they are triumphs of structural calculation. One can notice how 9-meter-tall steel bollards are driven with hydraulic force into unstable shifting sands and solid subterranean rock. How is it possible to pour 15-meter-high concrete walls while the Pacific Ocean strikes the coast with devastating kinetic energy? The process is only gaining momentum. To understand this, one must analyze the physical anatomy of these megastructures, ranging from the deep granite trenches of Arizona to the interlocking concrete tetrapods protecting Fukushima. Engineers utilize the raw strength of metal and stone to domesticate environmental instability. The assembly of these artificial boundaries originates long before a single pillar reaches toward the sky. In the United States, the primary obstacle is not found in policy, but in the complex variables of geology. One can notice the camera gliding along a frontier line that spans 3,200 kilometers, where the soil composition shifts radically at every interval of 1,600 meters. The equipment gradually maneuvers through soft sand deserts that threaten to submerge heavy machinery under its own weight. In specific regions such as Arizona and California, the Earth acts as a natural armor plate composed of solid granite and volcanic rock. It gets more complex further on. Heavy-duty drilling rigs must penetrate these layers to create stable foundations for the steel barriers. One can notice the dust settling in slow clouds as diamond-tipped bits grind through the stone. This ensures that the massive steel bollards remain anchored against both environmental erosion and physical impact. Each segment of the wall is integrated into the terrain with millimetric precision to prevent structural failure. The metal components are coated in specialized finishes to resist the corrosive effects of the desert sun and moisture. From here, the transformation moves to the next phase of processing. 9 meters is the height reached by the massive steel posts that must be anchored firmly against the relentless force of winds, capable of uprooting mature trees. Why must surveying teams drill soil samples and calculate exact elevations long before a single shovel of earth is moved? The stability of the entire industrial structure depends entirely on the geological composition hidden beneath the surface. Excavating the foundation serves as the first major physical confrontation in the construction process. One can notice how the equipment carves a continuous trench rather than a series of isolated holes. This is a precise vertical channel measuring between 60 and 80 centimeters in width. It only looks obvious to dig a shallow path, but in reality, the depth reaches between 1 meter and 80 centimeters and 3 meters. At the bottom of this trench, a technician would be surrounded by earthen walls nearly double the height of an average human being. Standard excavators perform the task with ease in soft soil conditions. However, the process is only gaining momentum as the terrain shifts toward impenetrable rock. The common excavator becomes ineffective when encountering the dense crust of the borderlands. Engineers must deploy heavy hydraulic breakers attached to large-scale excavating units to overcome this obstacle. These attachments function as pneumatic hammers the size of a passenger car, striking the rock surface with thousands of pounds of force to fracture the stone. The sound is ensurdecedor as the equipment gradually removes large fragments of debris. Progress is measured in mere inches during this phase of the work, but this is just the beginning. To accelerate this brutal sequence and maintain required tolerances, a machine known as the trencher is brought to the site. This apparatus utilizes diesel engines producing between 250 and 400 horsepower. It is equipped with a colossal chainsaw that cuts through hardened ground as if the material offered no resistance. One can notice the camera glides along the machine as its rotating blades slice perfectly straight walls. While excavators handle the initial rough removal, the trencher advances to deepen the trench to the exact level dictated by the engineering specifications. At the same time, the teeth of the chain pulverize any remaining rock, leaving the floor of the trench flat and clear of obstructions. It gets more complex further on. The equipment features a conveyor system that continuously ejects debris to the side of the excavation path. This mechanical beast completes work in a matter of days that would otherwise take weeks of manual labor. Hundreds of meters of trenching are processed in a single continuous movement. At first glance, the task of opening the earth seems complete, but in reality, the structural integrity must be reinforced immediately. The open wound in the earth is now leveled and ready for the next stage of fortification. Workers begin the installation of a steel cage composed of heavy vertical bars. The metal lays in an even layer as the skeletal frame takes shape within the deep channel. Transition to the next level. This reinforcement will eventually bind the concrete and steel into a singular, immovable foundation. 10 millimeters of thickness is the precise measurement of the steel walls forming the hollow square or circular bollards that serve as the backbone of the border structure. Why is a hollow design preferred over solid steel for such a massive project? One might assume a solid pillar would be more resilient, but the hollow engineering choice is a calculated strategic move. It significantly reduces the total weight for logistics, allowing heavy-duty trucks to transport a much larger volume of units across vast distances. Yet it conceals a structural secret related to the final stability of the barrier. It seems simple to transport these components, but in reality, the logistics require extreme caution. Each individual post weighs between 250 and 400 kilograms. They arrive at the site stacked in tight layers on heavy-duty cargo trucks, secured firmly with steel straps to prevent the massive tubes from shifting or becoming lethal projectiles during the arduous journey through the desert. But this is just the beginning. One can notice how the mobile cranes lift bundles of these 9-meter-tall posts from the truck beds, depositing them into designated storage zones with the hiss of hydraulic cylinders. The equipment gradually moves the steel to a nearby temporary fabrication area. Here, the process is only gaining momentum. High-power welding machines are utilized by technicians to fuse the individual posts into modular panels, typically consisting of 4 to 6 posts, depending on the specific width requirements of the segment. Assembling these giants on the ground, rather than attempting to align them one by one inside the trench, accelerates the installation timeline drastically. However, lifting a steel panel measuring 9 meters in height and 9 meters in width in an open desert environment remains an operation of exceptionally high risk. The crane hoist cable tightens as it begins the lift, and the massive panel starts to act like a giant sail. A sudden gust of wind can cause the multi-ton structure to oscillate dangerously in mid-air. 2 to 3 workers remain on the ground, gripping guide ropes with intense focus to counteract the wind and position the panel exactly over the waiting trench. Precision becomes the absolute priority the moment the steel enters the excavation. Engineers utilize laser levels and specialized tensioning tools to ensure every single panel stands perfectly vertical. The process does not end at this stage. A deviation in the angle of inclination of just a few degrees could compromise the structural integrity of kilometers of the wall, leading to physical gaps or structural weak points. Once the alignment is confirmed, the panel is temporarily welded to anchors at the base, holding it completely immobile. It only looks obvious that the structure is finished But in reality, it is merely waiting for the final transformation. 10 to 20 centimeters of reinforced concrete are poured directly over the metal backbone along the borderline. This creates a flat, stable, and incredibly strong foundation block that supports the colossal weight of the steel panels without risk of sinking or tilting. As the concrete cures and fuses with the internal steel cage, it forms a continuous foundation beam capable of resisting massive torsional forces. This ensures the wall does not yield under the relentless pressure of desert winds. Camión Betonera trucks arrive in a steady queue to discharge fresh concrete into the voids. The liquid stone flows into the base of the structure, locking the modular panels into their permanent positions. The material is ready to move to the next processing phase without haste. Thus, the steel and concrete reach the standard required for the final stage of the border barrier construction. 1 meter and 50 centimeters is the exact distance the concrete foundation extends outward beyond the steel perimeter in high security zones. Why is this subterranean expansion necessary when the vertical posts already provide significant structural integrity? It would seem that the depth of the steel tubes alone should suffice, but in reality, this horizontal platform functions as a distribution mechanism for the immense weight of the barrier. The concrete base transforms into an underground shield that prevents any attempt to bypass the structure from below. Concrete is poured directly into the hollow centers of the steel tubes, bonding the metal and the artificial stone. This creates a composite pillar that increases the overall resistance of the wall by an exponential margin as the mixture hardens. But this is just the beginning. High-pressure water jets are deployed across the surface to strip away weld residues and industrial oils. One can notice how the equipment gradually scours the metal to ensure that the anti-rust coatings and protective paint layers adhere with absolute precision. The camera glides along the top of the structure, where military personnel install razor wire coils with edges as sharp as scalpels. These blades make the prospect of climbing the fortification a nearly impossible feat of endurance. $12 billion is the staggering amount Japan has invested in coastal defense projects following the catastrophic events of 2011. The nation faces a relentless geographical adversary in the form of black tsunami waves that once leveled entire cities. Nearly 400 kilometers of massive seawalls are being erected along the Tohoku coastline to serve as a primary line of defense. Everything only gets more complicated when considering the height of these barriers. They rise 15 meters into the air, which is the physical equivalent of a 5-story building. This scale is designed to buy residents those few precious minutes required for a successful evacuation. Transition to the next level. At first glance, the construction of these walls seems like a straightforward engineering task, but in reality, the geological conditions of the coastline present a massive obstacle. Most of the shoreline consists of weak, sandy soil that loses all stability when saturated with ocean water. Building such a heavy concrete monolith on this geological soup would lead to the structure sinking or sliding directly into the sea. Engineers must stabilize the ground before a single drop of concrete is poured at the site. One can notice the intense activity of cleaning crews who are tasked with removing the massive piles of debris left behind by the previous disaster. The equipment gradually clears the path for the heavy machinery required to reinforce the foundation. The process is only gaining momentum as the site is prepared for the next phase of stabilization. From here, the transformation moves to the next phase of processing as the ground is readied for the massive weight of the seawall. 24 meters is the depth to which hydraulic excavators must descend to secure the stability of the coastal defenses. Why is such an extreme depth necessary when the structure above the surface appears sufficient? The answer lies in the physics of oceanic impact, where the invisible foundation must counteract the immense horizontal force of a tsunami. But this is just the beginning. It seems simple to dig into the shoreline, but in reality, engineers must constantly struggle against the unpredictable cycles of tides and heavy rainfall. The true scale of this Japanese engineering feat remains hidden beneath the surface. To prevent these massive walls from toppling under the weight of a giant wave, the foundations are designed with titanic proportions. One can notice how the excavation pits reach depths that exceed the height of the wall itself above the ground. This creates a structural iceberg made of reinforced concrete, where the majority of the mass is submerged to ensure absolute stability against shifting sands. The process is only gaining momentum. Engineers build temporary cofferdams and steel retention walls to block the sea from entering the construction zones. This creates artificial dry islands, where machinery can operate safely below the waterline. The sandy soil undergoes stabilization through the injection of layers of crushed stone and compacted sand. The equipment gradually reinforces the ground with deep concrete or steel piles. Upon this prepared base, a massive and wide foundation slab is poured, with the hiss of heavy pumps. It acts as a giant structural foot, providing a wide surface area that prevents the wall from being pushed backward by the weight of the sea. It only looks obvious that the wall stands on its own, but in reality this base plate anchors the entire system. Giolas of steel rebar, dense and complex in their geometry, are assembled to form the internal skeleton of the barrier. Giant molds are positioned around these steel frames as the concrete is pumped into the voids section by section. Each individual block reaches tens of meters in length. Everything only gets more complicated. The camera glides along the continuous barrier as it curves along the coastline, with each segment cured and interconnected. A simple vertical surface would absorb the full impact of a wave at once, which poses a risk of structural failure. Because of this, Japanese designers implement inclined surfaces and concrete steps to dissipate the kinetic energy of the water. One can notice how the water breaks against these tiers rather than hitting a flat plane. The defense does not end with the primary wall structure. On the side facing the open ocean, thousands of specialized concrete units are placed to break the initial surge. The melt of logistics and engineering continues as the barrier takes its final form. $27 billion in massive infrastructure projects, millions of tons of reinforced concrete and hardened steel, and hundreds of kilometers of physical barriers define the scale of these monumental engineering efforts. Why are these geometric blocks stacked so precisely at the base of the seawall? It would seem that a flat surface would deflect the waves more efficiently, but in reality, these complex interlocking shapes function as a sophisticated breakwater, forcing turbulent water to flow around their multifaceted surfaces and lose its destructive kinetic energy long before it makes contact with the primary structure. One can notice how the external face of the wall is shielded by a specialized armor layer. Giant cranes lift precast concrete panels into position, fitting them together like a massive puzzle to create a seamless protective skin. This secondary layer is critical for safeguarding the wall's core against the relentless erosion caused by salt water and the high-velocity impact of debris carried by storms. On the landward side of the structure, complex drainage systems are integrated into the design. These channels ensure that rainwater cannot accumulate and create hydrostatic pressure that might destabilize the foundation from behind. Over $27 billion have been invested in these barriers made of millions of tons of heavy concrete and industrial steel. When evaluating these two megastructures, a fascinating contrast in materials and strategic purpose becomes visible. The American steel structures prioritize height and transparency to manage human movement across the vast desert borders. In contrast, the Japanese concrete walls rely on sheer mass and depth to resist the raw physical force of the ocean during a tsunami event. Both projects stand as physical monuments to human determination and technical precision. They serve as evidence that with sufficient resources and advanced engineering, it is possible to draw a definitive line across the sand or the sea to protect established infrastructure. Whether the objective is countering human activity or natural disasters, these walls represent a continuous search for security within a chaotic environment. The equipment gradually moves away, but the engineering challenge remains. History demonstrates that the conflict between static engineering and the dynamic forces of the planet never truly reaches a conclusion. It only changes in its physical scale. 99 million tons of earth and rock are moved during these titanic efforts. Imagine the logistics of shifting an entire mountain using only manual labor and basic tools without the assistance of a single mechanical engine. This monumental exertion was not intended to construct a tomb for ancient kings like the pyramids of Giza. Instead, the goal was to achieve something far more complex, the resurrection of a dead landscape. In a region where the forests have completely vanished and the water has evaporated from the soil, local farmers work without capital or modern technology. The process is only gaining momentum as they begin the manual transformation of the terrain. Their goal is the restoration of the ecological balance through sheer physical persistence and basic structural modifications to the earth. The soil is moved bucket by bucket and stone by stone, as the landscape is reshaped to retain what little moisture remains. It is visible how the terrain changes shape under the constant movement of thousands of hands. This stage concludes the preparation of the ground, opening the road to the next phase of the reclamation. From here, the project moves into the active phase of reforestation and water management. The material is settled, and the foundation for the new ecosystem is finally in place. This concludes one of the key stages of the land restoration process. 106,000 acres of forest returned to life in a nation devastated by famine without the planting of a single new tree. Why did traditional reforestation efforts involving millions of dollars and countless saplings fail so consistently in this landscape? The answer lies in a phenomenon that contradicts standard environmental logic and requires a deep look at a period when the environment collapsed into a state of total degradation. Ethiopia sits upon the East African highlands and was not always the arid, dust-filled expanse depicted in the global news cycles of the 1980s. One can notice from historical records that this territory was once referred to as the Garden of Africa. Dense and vibrant forests previously covered more than 60% of the entire country, while deep river systems provided water to one of the most fertile regions on the continent. But this paradise entered a spiral of destruction. The equipment of human expansion and survival moved against the greenery until Ethiopia lost more than half of its forest cover in just a few decades. By the year 1982, the situation had reached an apocalyptic scale. Total forest coverage plummeted to a mere 3% of the landmass. Of the original 77,000 square miles of verdant life, only 12,000 remained. Where life once thrived, only a hard and dry crust of earth existed. But these forests did not vanish through a supernatural occurrence. They were pushed toward the abyss by relentless human pressure. One can notice how century-old trees were systematically felled for firewood, while entire woodland ecosystems were incinerated to create desperate, temporary agricultural fields. The process is only gaining momentum toward disaster. When the trees disappeared, the earth lost its protective layer. Without complex root systems to anchor the soil, the ground lost its capacity to retain moisture. The rain eventually stopped falling entirely. Rivers dried up into cracked beds, and the wind scoured away the remaining fertile topsoil, leaving behind nothing but a red, barren desert. At first glance, it seems simple to blame the climate, but in reality, the biological infrastructure had been dismantled. Then the inevitable consequence arrived in the form of the Great Famine of 1983. This was the most devastating tragedy in the history of the nation, claiming the lives of more than 1 million people in a span of only 2 years. The world observed the crisis in shock, yet no one possessed the technical knowledge to halt the hemorrhaging of an entire ecosystem. The earth was considered clinically dead, and this was not the limit of the despair. In the center of this nightmare scenario, when all conventional hope seemed exhausted, a radical idea emerged from the dust. Previous traditional attempts to salvage the land had failed miserably. International aid projects had exhausted millions of dollars to plant new trees across the plains. However, 90% of those young saplings died within a few weeks of being placed in the ground. The sun at 40 degrees Celsius effectively cooked the plants alive while they were still in the soil. If the heat did not kill them, the starving livestock consumed the small amount of greenery that remained. Planting new trees proved to be expensive, slow, and ultimately futile in the face of such extreme conditions. It was during this time that Tony Rinaldo, an agronomist working in the region, observed a detail that would shift the course of history. What everyone else perceived as mere weeds and dry scrub brush in the middle of the desert was not waste at all. The equipment of nature was simply waiting for the correct intervention to begin its recovery. This realization marked the transition to the next level of ecological restoration. 30 meters is the depth to which the massive, ancient root systems of thousands of living tree stumps descended beneath the hardened crust of the earth. Why did these deep structures remain viable despite the surface appearing completely barren? The soil acted as a protective layer, keeping the powerful roots in a state of stasis while they awaited a physical signal to resume growth. Nature was not extinct in this region, but rather occupied a state of deep dormancy. One can notice how the strategy for restoration relied not on importing nursery saplings from distant locations, but on the application of a simple pruning knife. This technical method, known as Farmer Managed Natural Regeneration, or FMNR, functioned with mechanical simplicity. It gets more complex further on. Farmers identified existing stumps within the landscape and systematically pruned away the weaker, spindly branches. They selected exactly 3 or 4 of the most robust trunks to protect and nurture. One can notice the absence of expensive fertilizers or external irrigation systems in this process. Instead, the trees utilized their established massive root networks to propel new growth rapidly toward the sky. But a critical physical limitation remained. It seems simple to prune a tree, but in reality, no biological growth occurs without a consistent supply of moisture. The water had long since retreated from this specific geography, leaving the soil compacted. To reverse this, the inhabitants of Humbo transitioned into the roles of geographic engineers. They operated without the assistance of diesel engines, heavy tractors, or state-funded financial resources. Their inventory consisted solely of weathered shovels, steel pickaxes, and a rigid collective will. The process is only gaining momentum. They analyzed the denuded hillsides to construct a precise mental map of hydraulic flow. By recalling the historical patterns of rainfall from decades past, they initiated one of the largest manual labor operations in agricultural history. Men and women hauled heavy basalt and granite stones under a relentless sun to assemble thousands of miniature dams and structural terraces. 99 million tons of soil were moved by hand during this period. One can notice the sheer scale of this figure, which represents a mass equivalent to hundreds of steel-framed skyscrapers. Every kilogram was transported bucket by bucket and stone by stone across the rugged terrain. The technical objective was to fundamentally alter the physics of the local topography. Laborers excavated infiltration ponds and carved precise contour trenches designed to intercept every millimeter of precipitation. At first glance, the terrain looked the same, but the hydrology had been completely re-engineered. When the rains finally arrived, the water no longer formed destructive mudslides that stripped away the topsoil. Instead, the liquid encountered physical barriers that forced the flow to decelerate and settle. This allowed the water to permeate the thirsty subsoil layers. The equipment for this task was human muscle, and the result was a calculated change in the Earth's absorption rate. Deep ravines, which previously functioned as open wounds where water escaped the landscape, were systematically blocked using stone dikes. The engineering logic was absolute. Not a single drop of rain was permitted to leave the site. Everything only gets more complicated. The dusty red earth gradually transformed into a massive, functional sponge. It became an underground reservoir capable of feeding the dormant root systems waiting in the depths. One can notice how the landscape began to retain its moisture levels, even between rain events. But the physical engineering of the land represented only 50% of the total effort. The remainder involved complex social engineering within the community structure. For the forest to successfully regenerate, the population had to implement a restrictive policy. They prohibited livestock from grazing freely across the hillsides, a decision that disrupted centuries of tradition. For generations, goats and sheep had consumed every emerging green sprout, effectively halting the natural cycle of the trees. The material environment was finally prepared for a total transition. Thus, the foundations for a new ecosystem were laid, moving the project into a phase of quiet observation. Thousands of tons of livestock once compacted the earth until it reached the density of solid cement. Why would a community choose to seal off their own hillsides and essentially lock away their primary source of sustenance and income? This decision represented an immense sacrifice for the local population, who were forced to prioritize long-term survival over immediate survival. But the sacrifice was only the first step in a calculated environmental strategy. They divided the landscape into 3 strictly defined zones to ensure total ecological control. The valley floors were reserved exclusively for irrigation systems. The middle slopes were designated for structured agriculture, and the hilltops were declared sacred and untouchable to allow for total forest regeneration. Silence eventually descended over the high slopes, as the constant rhythmic thud of hooves and the sound of hungry mouths tearing at the helva vanished. One can notice how biological processes began to shift once the mechanical pressure of the animals was removed. The response from the natural world was explosive and immediate. Throughout just one single rainy season, The local vegetation returned with a visible green fury. But this is just the beginning. Where there was once nothing but bare, scorched stone, dense clusters of shrubs began to crawl across the terrain. Within 5 years, the total vegetation cover in these protected areas increased by 200%. The iron discipline of the villagers had successfully bought the time that the ecosystem required to heal itself. The morning humidity began to linger for twice as long as before, effectively creating a cool microclimate that functioned as a biological magnet. It is visible how this new moisture attracted insects, which in turn drew in species of birds that had not been documented in the area for several decades. The complex chain of life was being reconstructed link by link. Everything only gets more complicated as the hydraulic balance of the region began to shift. Then the impossible occurred. Water returned to the landscape, not through the arrival of tanker trucks or the installation of plastic pipes, but by erupting directly from the earth itself. It is important to recall the 13 natural springs of the region, which had previously dried up completely, existing only as fading memories held by the village elders. Because of the new tree root systems and the strategically placed stone terraces, rainwater was able to infiltrate deep into the crust. The liquid moved through the geological layers, slowly recharging the ancient underground aquifers. 6 of those 13 dead springs began to pour out crystal clear water once again. At first glance, it appeared to be a seasonal fluke, but in reality, the flow remained constant. These springs now flow continuously throughout all 12 months of the year. The water follows its natural course through the newly restored environment, signaling the completion of the primary recovery phase. The material foundation for a stable ecosystem is now firmly in place, and the process continues without haste. 85% is the exact figure by which agricultural production surged once moisture returned to the parched earth. One can notice how dry riverbeds, once nothing more than cracked arteries of dust, transformed into gentle, consistent streams. This water deposits fertile silt along the banks as it moves at a steady pace through the landscape. The hydraulic cycle learned to remain within the soil rather than evaporating. Why did domestic life undergo such a radical transformation overnight? For decades, women walked for 5 or 6 hours under a relentless sun to retrieve single jars of stagnant, muddy liquid. Now, clean water sources operate near their homes because the earth has been rehydrated. The miracle proved the soil was never dead, but merely dormant. By healing the ground, the workers repaired the entire local climate cycle. But this is just the beginning. The return of water triggered a profound economic revolution that moved far beyond simple ecology. Average family incomes rose by 76% as the damp, nutrient-rich soil began to yield massive harvests. People successfully transitioned from a state of total dependence on foreign food aid to becoming active producers who sell their own goods in regional markets. Where hunger previously dominated the landscape, beehives now produce honey, and sustainable timber is harvested at regular intervals. The community even generates revenue by selling carbon credits to the United Nations. One can notice how the forest functions like a financial institution, generating compound interest in the form of biological life. It gets more complex further on. 106,000 acres in Ethiopia served as the initial blueprint for this expansion, which soon crossed national borders like a positive wildfire. In Niger, the application of this specific method, involving only knives and stones, transformed over 12 million acres of desert into productive agricultural land. In Burkina Faso, barren hillsides have evolved into dense forests that provide food for millions of inhabitants. The equipment used is minimal, but the scale is massive. At first glance, it seems that high-end technology is required to save the environment, but in reality, the process requires only scalability and a deep respect for natural systems. The camera glides along a landscape where 99 million tons of earth were moved by human hands alone. This effort did not result in a cold stone monument, but in a living foundation for future generations. Is it truly possible to create a forest without ever planting a single tree? The answer remains etched into the revitalized terrain of Ethiopia, where life persists beneath the surface. This conclusion marks the final stabilization of the local ecosystem. 5 billion gallons of fresh water flow every single day beneath a sun that offers no reprieve to the landscape below. Why would an industrial civilization attempt to thrive in a region where 98% of the soil consists of nothing but scorching sand? The answer lies in the engineering of a mechanical lifeline that defies the natural geography of the peninsula. At first glance, the desert appears as a void, but in reality, it hosts a complex network of steel and water, long enough to wrap around the entire planet Earth 35 times. One can notice how the heat distortion ripples over the dunes, where temperatures frequently climb to 122 degrees Fahrenheit. This environment is a high-altitude plateau that systematically blocks rain clouds, effectively preventing any moisture from the sea from reaching the deep interior. Under such conditions, large-scale human life should not exist according to any standard climate map, as there is not a single natural river or lake to provide hydration. For thousands of years, survival was a matter of pure chance and nomadic movement, but this is just the beginning. Modern industrial demands have created a thirst that the desert cannot naturally quench. Each citizen in this region has access to only 68 to 90 cubic meters of natural water per year. To understand the severity of this deficit, one must realize this volume is 5 times lower than the absolute water poverty limit established by the United Nations. The process of overcoming this scarcity is only gaining momentum. When compared to the average American who enjoys over 9,000 cubic meters, the scale of the challenge becomes clear. It only looks obvious that a nation would simply drill for more wells. But the ancient water cycles are finite and require a different approach. Nature does not require a complete reinvention, but rather the strategic provision of space to function alongside human infrastructure. This transformation from a desert of red dust into an oasis of green gold serves as physical evidence of industrial power when it is synchronized with the forces of the earth. The equipment gradually replaces the missing natural cycles with a constant pressurized flow. It gets more complex further on. Forgotten water cycles are merely waiting for the cessation of conflict between human expansion and environmental limits. The camera glides along the massive pipelines where the steel ribbon maintains the pressure required to move billions of gallons. One can notice the slow, rhythmic pulse of the pumping stations that keep the network alive. This is the greatest life support system in history, a miracle of metallurgy and hydraulics. Everything only gets more complicated as the demand for resources grows alongside the population. The molten flow of progress continues through the pipes, ensuring the desert remains inhabited. From here, the transformation moves to the next phase of processing. 3 weeks is the maximum duration a human being can survive without food, yet that window shrinks to a mere few days when deprived of water. Why did the inhabitants of this arid region turn their gaze toward the depths of the earth? Survival became a calculated struggle against biology as the surface offered no relief. They began to excavate deep into the shifting sands, searching for hidden liquid treasures locked in ancient fossil aquifers that required thousands of years of geological stillness to accumulate. Technicians initiated a massive drilling campaign during the 1980s. Thousands of drill bits pierced the desert floor, extracting trillions of gallons from the subterranean depths. This industrial expansion seemed like a mechanical miracle, and by 1992, annual consumption reached 7,500 billion gallons. To visualize such a scale, imagine a volume of water sufficient to fill more than 27,000 Empire State Buildings from the foundation to the roof. The equipment extracted the resource as if the supply were infinite. But this reliance rapidly transformed into a dangerous systemic addiction. One can notice how the geological reality mirrors the extraction of hydrocarbons. Fossil groundwater does not replenish itself through the natural cycle. It functions exactly like an oil well, where once the reservoir is empty, it remains vacant for eternity. The clock began to accelerate faster than any mathematical model had predicted. Within a span of only 25 years, the water table in the vital Al-Asa aquifer plummeted nearly 500 feet. This was a silent and invisible collapse of the internal pressure systems. By the year 2012, 80% of the total underground reserves, amounting to 132 trillion gallons, had vanished completely. The nation was effectively consuming its own future through the mechanical suction of the pumps. Desert agriculture, once viewed as a technological triumph over nature, was consuming 6,500 billion gallons by 2015. Everything only gets more complicated as the limits of the aquifer are reached. Authorities were forced to apply the brakes with maximum force to prevent a total dryout. Thirsty wheat fields were either abandoned or retrofitted with high-tech drip irrigation and precision moisture sensors. Agricultural consumption dropped by 40% following these mandates. City administrations imposed heavy financial penalties on anyone wasting a single drop of the processed liquid. It seems simple to manage demand through fines, but in reality, water conservation was merely a temporary bandage on an expanding wound. The population continued to grow, and the biological thirst of the city showed no signs of slowing down. They required a new source that could be considered truly infinite. But this is just the beginning of a much larger industrial shift. The only infinite resource surrounding their borders was the ocean itself. However, the sea is saturated with salt, and consuming it in its raw state is a biological death sentence. Success depended on possessing the specialized technology to tame the salt. The proposed solution required raw industrial power on a scale never before witnessed in the region. Engineers decided to boil the sea, a statement that is not a metaphor, but a literal description of thermal processing. One can notice the massive heat exchangers preparing to transform salt water into vapor to separate the minerals. This process involves turning the sea into steam and then condensing it back into purified water. It only looks like a small laboratory experiment, but in reality, it requires massive infrastructure. 75 million people depend on a colossal steel infrastructure that defies the natural limits of the desert. Currently, Saudi Arabia operates 41 massive desalination plants positioned strategically along the coastlines of the Red Sea and the Persian Gulf. Why has this nation invested so heavily in these titanic metal structures? While traditional sources of water are non-existent here, these facilities generate 3 billion gallons of fresh water every single day. This output accounts for 22% of the total desalinated water produced across the entire planet. This industrial scale is unparalleled globally. One can notice the immense disparity when comparing these figures to other developed nations. If one were to combine the capacity of every desalination plant in the United States, the total would amount to less than 1/5 of the Saudi Arabian production volume. It is important to consider that the American coastline is significantly more extensive, yet the concentration of engineering power, 99% of all contaminants, including even the smallest biological viruses, are successfully blocked by these barriers. Why is such extreme filtration necessary for a municipal supply? The water emerging from the secondary side of the membrane is chemically pure, having been stripped of microscopic threats and minerals alike. This ensures that the final product remains safe for consumption in a region where natural freshwater sources are non-existent. The beauty of this system lies in its mechanical efficiency. Modern energy recovery devices capture and reuse pressure that would otherwise be lost during the filtration cycle. It is visible how the high-pressure pumps work in tandem with these recovery units to minimize consumption. Because of this integration, newer plants require only 2.8 kilowatt-hours of electricity to generate 264 gallons of potable water. This energy expenditure is roughly equivalent to the power consumed by 10 light-emitting diode lamps, burning for a single hour. One can notice the scale of this silent revolution across the urban landscape of the kingdom. Today, 2/3 of the total water volume supplied to major cities originates from these high-technology membranes. Every single glass of water consumed in Riyadh has passed through these microscopic filters, which operate on a hybrid energy mix of conventional electricity and massive arrays of solar panels that glisten under the desert sun. But this is just the beginning. Creating fresh water at the coastline is merely the initial phase of the logistical operation. Most of the population resides far from the coastline, situated in the arid central regions of the country. How do engineers move the volume of an ocean across a scorching desert? This creates what is widely considered the greatest logistical challenge in the history of hydraulic engineering. Transporting liquid is physically taxing because water possesses immense weight, and the topography of Saudi Arabia is far from a flat plain. It only looks obvious to move water horizontally, but in reality, the geography presents vertical obstacles. Equipment must push millions of tons of water to cities and villages located hundreds of miles away, often situated at the summits of steep mountain ranges. The previous distribution network focused exclusively on the capital city and the holy site of Mecca. However, with the population of Riyadh expanding rapidly toward 8 million people and projected to reach 9 million by the year 2035, a more robust solution became a necessity. The process is only gaining momentum as the demand for a vital artery grows. Engineers could not utilize open-air canals, similar to those constructed by the Romans or implemented in modern-day California. Under a sun that routinely reaches temperatures of 50 degrees Celsius, the water would vanish through evaporation long before reaching its destination. Furthermore, the relentless desert wind would carry sand into the channels, contaminating the entire supply. The camera glides along the path where the solution was ultimately buried deep beneath the dunes. Instead of open channels, the kingdom opted to construct a river of steel. This network consists of massive sealed pipelines that are protected from both the heat and external debris. This closed distribution infrastructure has been officially recognized as the largest of its kind in the entire world, spanning thousands of miles across the sand. The metal remains cool beneath the earth as the massive volume of water flows toward the inland reservoirs. Molten energy and mechanical force have successfully conquered the distance, and the water now reaches the distribution hubs. From here, the transformation moves to the next phase of processing.